This video is about the rate of change. We're going to be able to calculate and interpret the rate of change, and we'll understand how to calculate and interpret the slope. So really we're going to talk about rate of change and slope. And I'm not exactly sure how much you learned last year, but we're going to learn it all this year. We'll build upon whatever you had. Rate of change refers to how a quantity is changing with respect to another quantity. So essentially what we're going to deal with is the independent variable and the dependent variable. So the rate of change is always a change in y. That's our delta, change in y. That means change. That it was change in x. You don't have to write it like that. So this is going to be our rate of change. So if I'm looking at this, so for example, if I'm looking at this example problem here, finding the rate of change, find the rate of change of the function by using the 2 points in the table. Any 2 points will work. You could use these two guys here or these two guys here. The book used 24 and 4, and they used 12 and 2. No big deal. Here's your x value. Here's your y value. The change in y over the change in x. So the change is the difference. You'll notice they're subtracting. It's the difference. So we'll talk about the formula in a second. So if I take my 24 minus 12, if this one was first, that will be second. This is my y here. This is my x here. Then my 12 here is my second y. This is my second x. So I call it y sub 2. Here's my first y sub 1. My first x sub 1. And while I'm thinking about it, the phrase that pays will be submarine sandwiches. From Mr. Sub. It's a Chicago thing called Mr. Sub. Oh, you can't see that. Mr. Sub, submarine sandwich. Okay. So anyways, y sub 2 and y sub 1, x sub 1. It doesn't matter how you set it up in terms of the y's, but if this is my first y here, this has to be my first x. Okay, if this is my second y here, this is my second x. And that's not absolute, but I just let you know this is my first y and second y. Okay, the coordinates for that. So when you go ahead and do that, find out the rate of change numerically. So I do 24 minus 12, which is 12. 4 minus 2, which is 2. 12 over 2, which is fine, or just 6. Okay, so this, I don't know what that means here. This means you can make 6 pancakes for each cup of flour. That's the rate. If I'm looking at this table, amount of flour per pancakes. The other thing you could do is just 6 times 6 is 36, 4 times 6 is 24. That's the rate. 2 times 6 is 12. I mean, if you can figure that out easy, that's one way of doing it. But here's the formula that works for it all the time. So go ahead and do the check. Well, that's not fun to do, but I did it without a calculator. Feels so old school. I picked 2 ordered pairs. I picked 15.77 and 4.75. This is going to be my y, because the cost is determinant upon how many gallons I put into the tank. So this is my independent variable right here. This is my dependent variable. I don't know how much it's going to cost. The cost will be 100% based upon what I'm putting in. So these are my x values, these are my y values. So this is my first y I chose, and the first x for the ordered pairs that I used over here, and then the second one I chose was 2407, this guy here. These two guys over here. So this is my second y and second x. Sub 2's. Okay. So just go ahead and do the math, and you get about $3.32 is the rate of change, or the actual price. Let's proceed. Okay. Let's take a peek at this graph over here. I'm going to compare rates of change about the Jackson High School Student Council budget. So let's look at this graph without reading anything else. Here's the school budget, student council budget. It's in dollars, so $2,000, $1,500, $1,000, $500. This obviously the scrunching means we're not going to show all the years that they're talking about beforehand. 2000, 2005, 2010, 2000, those are the years that they're looking at. So I have 2000 and 1350, 2005 and 1675, 2010 and 1550, and 2015, 1325. So I have that. As I'm reading this graph, it looks like it's increasing steadily here. Then the amount of dollars that we have over time between 2005 and 2010 is decreasing. It's decreasing even more. So they're losing money or spending it. However it is, the fundraising looks like they're not. Oh, actually, it's fundraising. I'm assuming they're raising money. I didn't really read this. Well, it looks like there's nothing else. They don't give us too much of anything else. Here's our dollars. It's a fundraising budget. increased. We had good money coming in, and our fundraising efforts have decreased over time. Now, fill in what you know. And then press pause and fill in what you know. So if I look at the change in budget, so here's my budgetary change in terms of the budget. $325 if it takes $1,675 minus $1,350, and 2005 and 2000. Now you could do the reverse. You could do $1,350 minus $1,675 and 2000 minus 2005. You'll get negative numbers. If we get a negative divided by negative is a positive, so still come with a positive value. So their budget. Oh, it's not fundraising. It's their budget. I'm interpreting this differently, but it says the council budget increased by $325 over 5 years. Again, I would take that as their fundraising. So, anyways. So this is their budget based on the fundraising. So okay, so the budget is how much they are going to spend, and then the fundraising how much they're going to raise. So obviously this is not the fundraising, this is the budget in terms of what they've spent. Okay. DocAm doesn't know how to read. Now you know that. Okay, good. So the rate of change is $65 per year for this segment only. It's going to change for the next segment. Here they want you to do the rate of change between 2010 and 2015. So this is the segment here, 2010 and 2015. Go ahead and fill out that work right now. I'll pause that. So when you run the numbers, you'll see that we have a negative value here, which makes sense because we're dropping, we're declining over time. So the amount of money that we're bringing in, our budget's also decreasing here by $45 a year. You have to have that negative sign to show that we're losing money. Okay, do the check right now. So I can't believe how cheap these tickets are for NFL tickets, but it's the Miami Dolphins, and well, enough said. But essentially here, define the price, the rate of change of tickets between 2009 and 2010. The value is going up, so I know I have to have a positive value, and it went up about $3.80. So you subtract the two differences in the 1 year. Okay. They want to know what the greatest change was. Well, between here and here, when the prices plummeted, and I can't remember why that would be. And then I know one of the years they went to that was a long time ago. But anyways, and then what's the negative values? Obviously, here to here is a negative value, and here to here is a negative value. So between this segment here and this segment here would be negative values. Okay, let's go ahead and continue on about our constant rate of change. So in terms of constant rate of change, we're going to take a look at these values and see what they happen to be. We want to find out if this is a linear function. If it's a linear function, it will have a constant rate of change. So for example, if I'm looking at this, there's no way this is a linear function. All right, it's not a straight line. There's a lot of straight lines together. From this segment to this segment, it's definitely linear. From this segment to this segment, it's definitely linear. Let me get my little hideout bears. From this segment to this segment, that's definitely linear. Same thing for over here. Here, it's definitely, now that's obviously the line right there, right? It's a horizontal line, and that from there to there, it's definitely linear. So when we're looking at the segments, they're linear, but when we look at the entire graph in its totality, it's not linear. So one of the things that they're going to ask you to do, or I'm going to ask you to do, is to take a peek at a table or a graph and let us know, is it a function? Is it linear? So if you look at this here, we want to see if this is a linear function. If it is linear, then you get to say the rate of change. Essentially, you want to find out, is there the same rate of change like we did here? If I were to go ahead and take this one here, 2 times 6 is 12. 4 times 6 is 24. 6 times 6 is 36. If that rate of change is the same, it will be a linear function. If it's different or varied, like this one for sure is, or this one for sure is, the entire graph, then it's not a linear function. It's still a function, it's just not a linear function, okay? So let's go ahead and find the rate of change with these values. Now, I'm finding the difference between this point here and this point here. So I use a -5 minus, now the difference is obviously from my formula, where I'm just finding the differences, okay? So ooh, it's a little blurry, a negative 5 minus a negative 3. That gives me a negative 2. And then 11 minus 8 is 3. Well, I did the next two ordered pairs, a negative 3 and a negative 1. I want to see what's going on for that. Well, it looks like these guys also have the same rate of change. Go ahead and find the rate of change for the rest of them there, between this guy and this guy and this guy and that guy, and see where we're at. Okay, so now we have, hopefully I'm recording. Let me double check to see that I'm recording. I think it should be recording. Recording is pause? Oh, recording is recording. Okay, good. All right, here we go. So let's, oh boy, I didn't finish it. All right, so I went through the other ordered pairs, and yeah, it came up 1, 2, 3. All of them came up negative 2 over 3. Again, I took my y sub 1 over this value here. I want to find the difference in two ordered pairs minus this guy here. This has to match up. So this first y with this first x, the second y with the second x. So when we find out the rate is the same throughout all the points, it's going to be considered constant. So I found that it's negative 2/3 is my rate of change. Therefore, if I have a constant rate of change for all those points, they call that a linear function. The function is indeed a line. It's not always going to be a line. It's not always going to be constant. Let's find out, caveat, what happens, and it's not. Go ahead and do example number 4. Okay, so I started this one off. I just did negative 4 and negative 1. So negative 4 and 22 and negative 1 and positive 29. And I got a negative 3/7. Then I went to the next order pairs, a negative 1 and 1. I mean, negative 1 and 29 and positive 1 and 36. Put that into the difference and find the rate of change. And that's negative 2/7. That's not the same. So because that's not constant, it is not the same. It's not constant. Therefore, it's not a linear function, okay? It's not a linear function. Because, and I just stopped. You could have kept on going, but I just stopped. I'm like, they want us to determine if it's linear. I found out right off the bat it's not linear, and then we go. Okay, this next one here, they want you to complete the table so the function is linear. So in order for the function to be linear, you have to have the constant rate of change. They've given you enough information with here to find out what your rate of change is. So find the rate of change and then put in the values for what it would be in order for it to be a linear function. Why do I keep on losing that? So annoying. Press pause and find it. Okay. So if you're doing this problem here, you realize that the rate of change is 6,050 cents. You'll get 325 over negative 50 cents, or negative 325 over positive 50. It depends on what values you had first. So I went through and I looked at the pattern. I'm like, well, if I subtract 50 cents going from this way here, it's not going to work. If I add 50 cents, I'll fill that up. That's a pattern. That for sure is a pattern. And here between 1075 and 750, I'm subtracting 325. So I want to subtract 325 from each one of these bad boys here. And then obviously add 325 onto here. $10.75 plus 325. That's an actual dollar onto that one there, right? So you're gonna get 14 bucks right over here. So of course my book answer has 1, which doesn't make any sense. I think the book answer is wrong. But here I'm just going to add 325. So they're increasing by 325 as we go. Here, decreasing by 50 cents as we go there. Okay, so that's the rate of change. It is linear, and it is a function. Okay, that is it for this one. And did I get a phrase that pays for this one here? Oh yeah, we got the phrase that pays. Okie dokie. I'm at the end of the limit here. Oh boy, here we go. Have a good day.